Hi everyone, this is Prof. K speaking, and today we're going to talk about how we can use integrated rate laws to determine half-lives for different reactions. And so the learning objectives for this video are to define half-life and then carry out related calculations using expressions derived from the integrated rate laws. So the definition of a half-life. A half-life is the time required for 1/2 of a given amount of reactant to be consumed. And we represent this as a variable that's T equals 1/2. And so you might have heard about this in a biology context or in a different class, but in other contexts, it can be used to say what the time it takes for half of a population to disappear or half of a radioactive isotope to disappear. And so we're going to use half-life in this course to talk about how much of some component is being consumed. So if we had a first order reaction and we start at a concentration of 3 molarity, then when we get to 1.5 as our concentration, the time where we have 1.5 is maybe somewhere here, which is close to maybe 15 seconds. On the other hand, if we have a second order reaction, then the time that it takes to go from 3 to 1.5 is shorter. And so maybe this is 8 or 9. So in order to calculate the half-life or the time it takes to get to a concentration equal to half of your initial concentration, you have to use integrated rate laws, which tell you how concentration changes as a function of time. So what we're going to do is we're going to take our integrated rate laws from the last video, and we're going to plug in a time of T equals 1/2, where our final concentration, or our A of T, is going to equal 1/2 A naught. So we're going to plug these into each of these expressions, and I'm going to do the math and show you what the half-lives are equal to, so that for different types of reactions, you're able to calculate what the half-life is. And if you're ever faced with a different integrated rate expression, you can always plug this in and T equals 1/2 N and solve for a half-life. So for a 0th order reaction, our integrated rate law is AT is equal to the initial concentration minus K times time. So if I plug in 1/2 the initial concentration for AT, and I plug in T equals 1/2, I get the expression that 1/2 of the initial concentration is equal to the initial concentration minus KT of 1/2. So I can subtract a 0 from both sides, or if I want to, I can subtract KT and then subtract half of the initial concentration, and I get K of the half-life times the half-life is equal to 1/2 times the initial concentration. And so then all I have to do is divide by K, and I get that the half-life for a 0th order reaction is the initial concentration divided by 2 times the rate constant. And so if I know the initial concentration and the rate constant, then I can tell you the half-life. If I know the half-life and the initial concentration, I can tell you the rate constant. And if I know the half-life and the rate constant, I can tell you the initial concentration. So this is an expression that helps us describe how long it takes for half of the initial concentration to go away. For a first order reaction, our integrated rate law is natural log to the concentration at some time is equal to natural log of the initial concentration minus the rate constant times time. So once again, I plug in T equals 1/2, and I plug in this final concentration of 1/2 of the initial concentration, and I get an expression that looks like this. And so I can subtract the natural log of the initial concentration from both sides, and I end up with an expression that is negative KT to the 1/2 is equal to the natural log of 1/2 times the initial concentration over the initial concentration, because when I subtract, then it ends up in division in this. And so I just wrote the concentrations here so as to not skip steps, but you might realize that this should take the form of the half-life is equal to 1 over -1 over the rate constant times the natural log of 1/2. And some people will write the half-life like this, and others will just do the math, take the natural log of 0.5 or 1/2, and get that the half-life for a first order reaction is equal to 0.69 over K. And so the half-life is always going to be a function of the rate constant. For a second order reaction, we have a different integrated rate law that we once again plug these values into, and we get 2 over A. And so if you plug a fraction into a denominator, the denominator switches to the numerator, so that's why I get 2 over the initial concentration is equal to 1 over the initial concentration plus KT 1/2. And so if I subtract 1 minus A from both sides, I'm left with 1 over the initial concentration is equal K times the half-life. And so all I have to do is divide by K again, and I get that the half-life for a second order reaction is equal to 1 over K times the initial concentration. So overall, we do the same process for each of these, and we get different half-lives because there's a different functional dependence of concentration on initial concentration and the rate constant and time. So there's a table in the book that summarizes what we've talked about in these past couple videos, but ultimately we started with some rate that helped us identify how concentrations change for different materials. And we use that to determine an integrated rate law. And that helps us see what sort of plot we could use to get a linear fit and extract rate data from. And the slopes of those plots are related to the rate constant slightly differently because the functional forms of each equation are slightly different. And as a result, the half-lives, or the amount of time it takes for your final concentration to be half of the initial concentration, also has a different dependence on initial concentration in K. And so being able to identify what a reaction is from its data, or being able to calculate concentrations at different times, is sort of the goal of this section, so that we can make predictions about what's happening in our systems, and we can identify what it means to be a first order reaction, a second order reaction, and do interesting calculations from there.